In the previous lecture, we studied designing algorithms. We learned how to create step-by-step solutions for a problem. Today, we will study growth of functions. This topic helps us to understand how an algorithm behaves when the input size increases. Even a well-designed algorithm can become slow if its growth is poor. First of all, let's understand what is growth of functions. Growth of functions tells us how the time or space of an algorithm increases as the input size increases. We don't calculate the exact time, we only study how fast it grows. For example, when we write a program, the input size can be small or very large. Some programs remain fast, some become slow, and some become impossible to run. So, this change in performance is called growth of functions. Why do we study growth of functions? We study growth of functions for three reasons. First one is to compare the algorithms, and second, to know how algorithms behave for large input sizes. And third one is to choose the better algorithm. For example, two methods solve the same problem. One becomes slow when the data increases, while the other remains fast. So growth helps us to choose the fast one. In algorithms, the input size is represented by n. N means the number of items. For example, if we search a name in a list, so n is the number of names in the list. Relation with algorithm analysis. Growth of functions is the base of algorithm analysis. It helps us to describe the algorithms using big O notation, omega notation, theta notation. These notations describe how functions grow. Now let's see the common types of growth of functions. This growth types helps to understand how fast an algorithm runs when the input size increases. Remember, we are not measuring the time in seconds, we are measuring how the time grows. Constant growth, big of 1. Constant growth means the time remains the same no matter how large the input is. For example, accessing a value from an array using its index. In this growth, the input increases but the time doesn't change. Second is the logarithmic growth. Logarithmic growth means time increases very slowly. For example, binary search where we keep dividing the data into half. Logarithmic growth is very fast for large input. Third is the linear growth, big of n. Linear growth means the time increases step by step with the input size. For example, in linear search, checking the elements one by one. Next is the linear thematic growth. Linear thematic growth is slightly slower than linear but much faster than quadratic. For example, in merge sort, which divides the data and then combines it. So linear thematic growth is used in efficient sorting algorithms. Next is the quadratic growth. Quadratic growth means time increases very fast as the input grows. In bubble sort, where every element is compared with every other element. So quadratic growth is not suitable for large input. Exponential growth. Exponential growth means time doubles with every new input. For example, generating all the possible subsets using the recursion. So exponential growth becomes slow very quickly. Last is the factorial growth. Factorial growth is the slowest and the worst type of growth. For example, solving the traveling salesman problem using the brute force. So factorial growth is impossible for the large input sizes. As the input size becomes large, the order of growth from best to worst is constant growth is better than the logarithmic growth, and while the logarithmic growth is better than linear, and linear is better than linear arithmetic growth, and linear arithmetic growth is better than quadratic, quadratic is better than exponential, and exponential is better than the factorial. Lower growth means better efficiency. Why growth of functions matters? Suppose two algorithms solve the same problem. Algorithm A is the linear growth and algorithm B is the quadratic growth. For small input, both look fast, but for large input, quadratic growth becomes much slower. This is why growth rate matters more than actual running time. So growth of functions shows the performance and lower growth is always better. So today we learned about growth of functions, why growth of functions important, common types of growth of functions. We saw that some algorithms grow slowly and some grow very fast as the input size increases. Always remember lower growth means better performance. When the input size becomes large, the growth rate matters more than the actual time taken. This is why choosing the right algorithm is very important in programming. Now here is a question for all of you. If two algorithms solve the same problem, which one would you choose for large input, linear or quadratic? Write your answer in the comments. In the next lecture, we will see how to apply these concepts to real algorithms. Thank you for watching and keep learning.